This lecture discusses the normal approximation to the binomial distribution. Consider this problem. Let x be the number of heads when tossing a balanced coin 100 times. Find the probability that x falls within 10 and 70, inclusive. We have known that x is a binomial random variable with parameter n equals 100 and p equals 0.5. This problem asks for the probability of x greater than or equal to 10 and less than or equal to 70. To solve this problem, we need to calculate the probability of x equals 10, x equals 11, and up to x equals 70 separately, and then add these probabilities together. It is tedious and almost impossible to calculate by hand. Is there any easier way to solve this problem? We have seen these three plots before. They are the probability histogram for binomial random variables when n equals 3, n equals 10, and n equals 50. As n increases, the shape of the distribution becomes more and more closer to a normal distribution. This motivates us to think whether it is possible to approximate the probabilities of a binomial random variable by the probability of a normal random variable. The answer is yes. We will discuss how to approximate binomial random variable using a normal random variable. Recall that a binomial random variable is determined by two parameters, n and p. The mean of a binomial random variable is n times p. The standard deviation of a binomial random variable is the square root of n times p times 1 minus p. A normal distribution is determined by its mean and standard deviation. A natural idea is to approximate a binomial random variable by a normal random variable with the same mean and deviation, standard deviation. For example, a student is taking a true-false exam with 10 questions. Assume that the student guesses at all 10 questions. Therefore, the probability of correctly answering one question is 0.5. Let x denote the number of correct answers by the student. Then x is a binomial random variable with parameters n equals 10 and p equals 0.5. We can calculate the mean of x is 10 times 0.5 equals 5. The standard deviation is the square root of 10 times 0.5 times 0.5 equals 1.58. Find the probability that the student gets either 7 or 8 answers correct. We first calculate this probability using the knowledge we learned for binomial random variables. First, write the probability function for binomial distribution. The probability of x equals x is 10 choose x times 0.5 to the power of x times 1 minus 0.5 to the power of 10 minus x. The problem asks for the probability of x equals 7 or 8. We need to calculate the probability of x equals 7 and the probability of x equals 8 and then add them together. For the probability of x equals 7, we replace x by 7 in the formula for the probability function. For the probability of x equals 8, we place x by 8 in the formula. The probabilities are 0.1172 and 0.0439, respectively. Their sum is 0.1611. So this is the answer to this question. The bottom figure plots the probability histogram of the binomial distribution and the density curve of a normal distribution. The normal curve has the same mean and standard deviation as the binomial random variable. The normal curve is smooth, but the edge of the probability histogram of the binomial is zigzag. They look similar but not identical. First, we cannot approximate the probability of a normal random variable equals 7 or 8. Recall that for a continuous random variable, the probability equals to a single value is always 0. We need to calculate the area between two values under a normal curve. Notice that for the binomial distribution, its probability at a certain value is displayed by a rectangle. Look at the rectangle corresponding to 7 and 8. A portion of the rectangle are above the normal curve. However, in some places, the rectangles are below the normal curve with a gap. Just imagine that if we cut off the portion above the normal curve to fill the gap between the rectangle and the normal curve, we approximately convert the binomial probability histogram to a normal density curve. This means that the area of the two rectangles is approximately the area between 6.5 and 8.5 under the normal curve. The correction for continuity is an adjustment required when approximating the distribution of a discrete random variable by a continuous random variable. More clearly, in this problem, it means that we do not approximate the probability using 7 to 8, but using 6.5 to 8.5. We offset the value by 0.5 to increase the accuracy of approximation. The small table here lists the x value, z-score, and the corresponding probabilities. When x equals 6.5, the z-score is 0.95, and we use the standard normal table to find the probability to be 0.8289. Similarly, when x equals 8.5, the corresponding probability is 0.9868. The difference between these two probabilities yields the probability of the shaded area, which is 0.9868 minus 0.8289 equals 0.1579. Compare it with the answer in the previous slide. They are close. Not every binomial distribution can be approximated nicely by a normal distribution. In this slide, there are 9 probability histograms for different binomial distributions. Different rows correspond to different values of n. The first row has n equals 5. The second row has n equals 10. And the third row has n equals 20. Different columns correspond to different value of p. The first column has p equals 0.3. The second column has p equals 0.5. The third column has p equals 0.8. We can observe that when n is large, the shape looks more like a normal distribution. When p moves away from 0.5, the shape deviates from the normal curve. As a summary, in order to get good approximation, we expect that n is large. Additionally, if p is away from 0.5, we may require an even larger value of n. The rule of approximation is summarized in this slide. To approximate binomial probabilities by normal curve areas, first identify parameters n and p of the binomial distribution. Recall that n is the number of ballooning trails and p is the probability of success. Continue only if both n times p and n times 1 minus p are 5 or larger. Calculate the mean and the standard deviation of the binomial distribution. Make the correction for continuity and find the required area under the normal curve. Here are some comments on correction for continuity. For correction for continuity, we will add 0.5 or subtract 0.5 to make sure that the inequality contains the original whole numbers. For example, if we want to approximate p, the probability of x less than 16, notice that this inequality x less than 16 indicates the integers 0, 1, 2, and up to 15. We approximate it by the probability of x greater than or equal to negative 0.5 and less than or equal to 15.5, because this inequality contains the same integers. On the right-hand side, we subtract 0.5 from 16. On the left-hand side, we just want to make sure that this inequality does not contain any negative integers. To approximate the probability of x greater than 12 and less than or equal to 16, notice that this inequality contains 13, 14, 15, and 16. Therefore, we approximate it by the probability of x greater than or equal to 12.5 and less than or equal to 16.5. On the left-hand side, we add 0.5 to 12. On the right-hand side, we add 0.5 to 16. Let's look at one example. The probability that a person of age 20 years will be alive at age 65 years is 0.8. Suppose that 500 people of age 20 are selected at random. Then the number of people who are alive at 65 years old follows a binomial distribution with parameter n equals 500 and p equals 0.8. Before applying the normal approximation, we need to make sure that n times p and n times 1 minus p are larger than 5. Here, n times p equals 500 times 0.8 equals 400, and n times 1 minus p is 100. Both are larger than 5. Therefore, normal approximation is appropriate. We can calculate the mean and the standard deviation of x. Following the formula, the mean mu is n times p, or 400. The standard deviation, sigma, is the square root of n times p times 1 minus p. The answer is 8.94. To answer the first question, find the probability that exactly 390 of them will be alive at age 65. Here, we want to find the probability of x equals 390. It involves only one integer, 390. We need to apply the correction of continuity. We need to find an inequality that includes only one integer, 390. Clearly, x greater than or equal to 389.5, less than or equal to 390.5 works. Here, we essentially subtract 0.5 from 390 and add 0.5 to 390. Now, the problem becomes, what is the probability of x greater than or equal to 389.5 and less than or equal to 390.5. Assuming that x is a normal random variable with mean mu equals 400 and standard deviation sigma equals 8.94. The steps to find such a probability are first to calculate the corresponding z-scores and then identify the probability using the standard normal table. To get z-scores, we need to subtract the mean and then divide it by standard deviation. The z-score for 389.5 is negative 1.17. The z-score for 390.5 is negative 1.06. Using the standard normal table, the corresponding probabilities are 0.1210 and 0.1446. The probability we want is the difference between these two probabilities. 0.1446 minus 0.1210 equals 0.0236. Therefore, the probability that exactly 390 of them will be alive at age 65 is 0.0236. Find the probability that between 375 and 425 of them inclusive will be alive at age 65. This question asks for probability of x greater than or equal to 375, less than or equal to 425. This inequality contains integers from 375 to 425. Recall the rule of correction for continuity. We want to add or subtract 0.5 such that the inequality contains the same original integers. To achieve this purpose, we need to subtract 0.5 from the left-hand side and add 0.5 to the right-hand side. We need to approximate the probability by x greater than or equal to 374.5 and less than or equal to 425.5. After we identify this inequality, the remaining steps will be similar to the previous slide. We first find the corresponding z-scores, and then find the corresponding probability, and then calculate the difference between these two probabilities. The table on the slides lists the detailed calculations. The z-scores are negative 2.85 and 2.85, respectively. Their corresponding probabilities are 0.0022 and 0.9978 using the standard normal table. The answer for this question is the difference of these two probabilities. 0.9978 minus 0.0022 equals 0.9956. In order to assess the accuracy of this approximation, I use Excel to evaluate the probability. If we treat x as a binomial random variable, the exact probability is 0.9957. If we use normal approximation, the probability is also 0.9957. They are equal. The number is slightly different from the number we calculated by hand. It is due to rounding errors.